Okay, we'll get started. So what we're doing today, we're going to continue with separable equations, which is going to lead us into doing models for population growth. We've already experienced some of the population growth, but we'll work some problems out with that. So here's a problem. dy and dx equals e to the y sine x. Good problem to kind of warm up with. This is from 9.3. And can you find the solution y? Can you find a solution to this differential equation? Can you find the y equals? I'll just say solve for y explicitly. Will that work? That means we'll get y equals 2. And on this first problem, you'll notice I'm not giving you an initial value. So that means we're just going to have to leave the answer as plus c, plus constant. Leave the final answer. Hey, so step 1, we got to solve this by using separable equations. And that means let's get the y's on the left side. Let's get all x's on the right. So that'll be easy. What? Divide e to y? E to y or v to y? Multiply dx, sine x dx. So far so good? Is it okay to have to pull the shade down or anything?
That's cool.
Oh, cool. Alright, now everyone, we've separated, let's integrate both sides. Integrate this side with respect to y, integrate that side with respect to x. But that's, how do you do that? Isn't that e to the negative y? So let me write e to the negative y dy. Help me integrate that, and we're going to integrate this sine of x. That's going to be easy. So I'm going to take a u sub. Let u equal that negative y. Right? So what's du? Negative 1 dy. So negative du equals dy, right? So all that's going to happen here is when you're doing this integral here, you'll get a negative e to the u du. And what's the integral of e to the u? E to the u. So we get negative e to the u. Put your u back, which was what? Alright, we get negative e to the negative y. We'll just put the plus constant on the right. We'll just put the plus constant on the right. Is everyone okay with the left side? I know you're going to find the right side a lot easier. Integral sine positive or negative cos?
Negative.
Negative cos. There, I'll put the plus constant. And I'll write it again. So now it just comes down to us solving for y explicitly. We got to get this y out of here. The first thing I notice, both of these are negatives. So I think we should multiply a negative on both sides. Is everyone okay with that? I mean, I'm trying to solve for this y. It's like, that's negative, that's negative. How about let's multiply a negative 1 on the left, multiply a negative 1 on the right. This will just make it positive. That allows us to do the natural log of both sides, right? This becomes cosine x. Oh, this becomes minus c then, right? Some of you still just write plus c, don't you? That's okay if you left that plus c because it's an unknown constant. But I'll write minus. Alright, you ready? What do we do to both sides? Natural log. Natural log to the left, and natural log to the right. And then we'll have this negative y. Natural log, I gotta put a parenthesis around this whole thing. Cosine of x minus c. I'll move that to the front. Yeah, because I don't have e to negative y, there's negative y in it. So, what is my final answer? Negative y equals that. Then y equals negative natural log cosine of x minus. There you go. We solve for y. Explicitly. Let's see if you have any questions on that. So you notice even throughout 9.4, we'll still be doing separable equations when we do models, but I still want to do some more of these problems in section 9.d, the separable equations. Solve for y explicitly using separable equations. Was someone okay with that? Okay, cool. We're going to do some application problems before we do the models for population growth. So this next problem models a current in an electric circuit. Let me put this equation down. All right, L times di dt plus Ri equals E of t. This models an electric current. I of t is the electric current. The units are amperes. I'd like to put a capital A, but that's this differential equation here. You can see right there that rate of change of I with respect to t, with respect to time. This models an electric, a current in an electric circuit, and I'm going to give you some values that are presented in this electric circuit, and it's going to allow us to go through here and use separable equations and solve for I. We're going to actually go and find a solution to this I of t and isolate that, make that explicit. So to start with, let's go over some of these numbers. Well, they give this R stands for the resistance, and that's given to you. So the resistance is 12. Now when assembly uses this, it's ohms, so that's 12 ohms. Yeah, I'll write it like that, 12 OHMS. That's really the Greek letter omega. But we just refer to that in terms of resistance. The units are ohms. So R is 12 ohms. What else do they give us? They give us the inductance. And when the inductance is 4 henries. The letter for inductance is this capital L. So that L stands for the inductance. And the L is 4 henries. You can just put 4. I'm just going to make a note. That's the inductance. So that was the resistance. Anything else? Oh, they said it's a constant voltage. Of 60 volts. And that's what we can book for E of t. That will be. So let's plug all these numbers in here. And then we're going to solve for I. And there is an initial value given. I'll give that to you. All right, that's 4. di dt. Here's our differential equation. R is 12. You notice we don't have I. di dt, we've got an I, and this is the 60. But what you and I are going to do is we're going to keep going through separable equations, and we're going to get I of t equals, right? We're going to find a solution that models that models the current in that electric circuit. Now, one more thing. What did they? And I got the problem everyone told. They did say this: the switch is turned on when t is 0. Well, what they're saying is this: the current at t equals 0 is 0. That's what they're saying. So put that down. That's the initial value. We're going to use that to get the constant. So we got the R given to us. L, constant voltage is 60 volts, but they did say the switch was turned on at time equal to 0. That just means at t equals 0, I will be 0. All right. So let's get this thing rocking and rolling through separable equations. The first thing I see, 4, 12, and 60. Can we simplify the numbers on both sides? Love it. I think the same way. These numbers are kind of big, but they're all even. Want to divide out of 4 on both sides? All right. di dt plus 3i equals 15. Let's get the i's on the left and the t's on the right. Well, how do we do that? Man. Sure that looks presentable. DI. We got to get the i's on the left, the t's on the right. This is respect to time. We're going to put the lowercase t on the right. Well, I can subtract the 3i on both sides, right? di dt equals 15 minus 3i. Or, negative 3i plus 15. And I think you all know how we can do this. I'm trying to get all the i's on the left so we can separate this. Separable equations. So can I just divide this? Yeah, that whole negative 3i plus 15, we surely can. Here's what I do. This is my suggestion. When it comes to integrating both sides, I always try to avoid a u sub on the left if I can. If I can't, it's no big deal. You've been doing the substitution rule so many times in this course, you understand how to do it. But if I can avoid it, I will, to just limit the amount of math I have to do. Make it easier, facilitate it. So I'm going to factor out that negative 3 there. Is that negative 3? I'm just going to factor it out and leave it up on the right side. What would be in the parentheses then? I do want to point out, you don't have to do this. I suggest it because I want to avoid a u sub over here. You probably can see you've got a natural log coming up in a second on an antiderivative. What would be in the parentheses? I minus 5. Very good. But this allows me, when I divide that over here, I'll have di over, look, I minus 5 equals negative 3 dt. And I'm just like, oh, cool. That's an easy antiderivative. Integrate net respect to I. Do you all notice that's a natural log? The integral is just going to be the natural log of I minus 5. Now, what if I brought this over? I would have had to do a u sub. I would have done a u sub. I would have let u equal that negative 3i plus 15 on the left and done a u sub and still got a natural log. But it would have been more work. That's why I thought, hey, might as well factor that out first. Is everyone okay with that? Hey, cool. Hey, you ready to integrate? Integrate that, integrate that. Integrate, integrate. What's the integral of negative 3d? Oh, that's negative 2t plus c. This integral, natural log of I minus 5. And I'll continue up here since I'm getting a little bored there. Almost getting the I. We perform the integral of both sides, right? You can think of this as 1 over I minus 5 if it helps everyone. Look at that. I should make sure that's a 1, not an I. That's a 1, right? 1. 1 over I minus 5 di. That would be the integral. What do you do next?
Raise it to e.
Yes! E raised to the left side. E raised to the right side. So I'm going to e to the natural log of I minus 5 equals e raised to the negative 3t plus c. This seems to happen on a few of these problems in this section. Happens a lot with circuits here. Well, that just becomes I minus 5. And I'm going to take the bars off because we got this constant here. Do you remember how I can write this?
You can make it e to the negative 3t times e to the c.
Okay, I'm going to write that. You said you can make this e to the negative 3t times e to a c. Now, what can I make the e to the c?
Just c.
Just c. And if you just want to go directly to that point, in your work or on a test, that is totally fine. That this just becomes c e to the negative 3t. Does anyone see that? But she worked it out carefully. She said that's that. But e to a constant, 2.718281828 raised to a constant is an unknown constant. We can call it a constant, big C. And I think we got it. Well, we got everything but C. This models the current, but we just got to get C. And how do we get that constant C? Right there. This is this is called the initial, I'll put IV. That's the initial value. You can consider this an initial value problem. They gave us initial value so we can find that constant C. So let's go plug this in. What's the current? 0, it's in amperes. You're like 0 amperes equals C times e to the negative 3 times a 0. That's t. And that's lowercase t right there. So I'll plug that in. 0. I'll just put a 0. Plus a 5. So is C 5 or negative 5?
Negative 5.
Good. Very good. That's 1. So C is equal to negative 5. There we go. Here's the answer. I'll even write it as a function of t. I as a function of t. Here's your current. This models the current in this electric circuit. Negative 5 e to the negative 5t. No, it's negative 3t, right? Oh, thank you. Negative 5 e to the negative 3t plus a 5. And there it is. That's what we're looking for. That models the current. Oh, go ahead.
Why is negative 5? So e
Oh.
to the 0 is 1.
So c times 1 plus 5 equals 0, and then you got to solve for constant c. I'll even write that. C plus 5 equals 0. Solve for c, subtract 5 on both sides, and c equals negative 5. Very good.
What's the point of giving you the units when it's not like
I know, you can ignore that. I know you what you do it. That bugs you. The units, you know, the Henrys. You know, this is in ohms, and you're like, I'm just plugging these numbers in. You're right. That's okay. I'm with you, Joy. Don't let that bug you. And hey, if you're wondering this right here, this here is like, what's the units for I? It's in amperes. And if you want to, they just put a big A for amperes.
Does amperes do ohms, Henrys?
Yeah,
volts
exactly.
convert
Don't have
to
to worry about it.
amperes?
Good question. But these electric circuit problems, it all depends. Like sometimes, you know, it depends on what the resistance is and what the inductance is, etc. But don't let it bug you. Let me just put those numbers in there. Hey, one other question. Even the author asked this. Just an extension question. Can you find the limiting value of this current? I mean, can you find the limit as t approaches infinity? What's going to happen with that current? As time just goes on and on and on. So what would happen to this? That'll approach 0, right? Does everyone agree? Excellent. E to the negative 3 times 0, infinity. That's approaching 0, 0 plus 5. What's this heading towards? 5 amperes. So if you want to see a graph, it's like, what's going on here? This is at 5 amperes, and this current started at, let's see, at time equal to 0 was 0. Remember I 0 equals 0? And then it just kept approaching that horizontal, that horizontal asymptote, but that's the limiting value of the current. And Joey, don't let the ohms, the Henrys, even the volts. Hey, we're going to do another one. These are all leading up to models for population growth. Great job with that. Let's do one with Newton's law of cooling, just because it's so cool. We'll do one more from 9.3. How about Newton's law of cooling? I'll state the law. I'm going to give you some values, and then we'll write this out. Okay. Newton's law of cooling. Newton's law of cooling says that the rate of temperature is proportional. The rate of cooling, or the rate of change of temperature, the rate of cooling is proportional to the difference between the temperature and the surrounding environment's temperature. So I want to give you an example just to start out with. Let's just say a really hot cup of coffee. Let's say it's the cup of coffee is 95 degrees Celsius, and it's put in a room where the temperature is 20 degrees Celsius. Okay, so we all know what's going to happen. You put the coffee in there, A few hours later, what's it gonna do?
lukewarm.
Yeah, it's gonna approach this 20 degrees, isn't it? It's really hot right now, ooh, tastes good, all that stuff. It's just gonna keep cooling, that's Newton's law of cooling. So let me state it again, we'll write it out. The Newton's law of cooling says that the rate of cooling is proportional to the difference between the temperature of the object, in this case coffee, and the temperature of the surrounding environment, right? This would be the same thing if you took something warm and you put it in the fridge, right? So, let me write this out again. Rate of change of temperature with respect to time, the rate of cooling, is proportional to the difference between the temperature of the object, I'll use big T. In fact, you don't see that dy right there? How about for our problem, we could use y and t. How about we use big T for temperature and lowercase t for time? Does that sound good? So the rate of change of temperature with respect to time, the rate of the cooling, is proportional to, there's the K for is proportional to, the difference between the temperature of the object and the room temperature, what I'm just going to call room temperature R. But our goal is to model this temperature of the coffee, which means find an equation for T. We're going to take this all the way down and go T equals blah, 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 blah. So we want to model the temperature of that coffee. They got this problem out of the book. They did give one more piece of information, so I'm going to read it to you. They said, suppose the coffee cools at a rate of 1 degree Celsius per minute when T equals 70. So I'm just going to write that down. Suppose the coffee cools at a rate of 1 degree Celsius per minute when the temperature of that coffee is 70 degrees Celsius. All right. So these two pieces of information, everyone, is going to allow us to help us get all the, there's a couple constants going on here. Not only going to have to find, don't we usually get like a C or something like that? We're going to have to find that constant K. Well, let's start out. What's R? Yeah, very good. They gave us R. Does someone see it? R is the room temperature. The temperature of the environment. That's at 20 degrees. I'm going to write that for you. I mean, we could have waited if